In this video, I am going to start talking about some reactions of alcohols. So in earlier videos, I talked about reactions that we can use to synthesize alcohols, but this one will be reactions that we can actually do with the functional group of alcohol. And so these are some of the types of reactions we can do with alcohols. This video is going to focus on this one right here. So we're going to look at oxidation of alcohols, so turning them into ketones, aldehydes, and carboxylic acids. So these are some of the oxidation and reductions we can do with alcohols. So we oxidize an alkane, for instance, we can turn it into an alcohol. But what we're mostly going to be talking about is turning, say, a primary alcohol into an aldehyde or a carboxylic acid, or turning a secondary alcohol into a ketone. So those are the oxidations that we will be mostly concerned with here. So oxidation is the addition of oxygen or O2, or the addition of a halogen, or the loss of hydrogen, where reduction is the addition of hydrogen or of a hydride, loss of an oxygen or O2, or loss of a halogen. And so neither would be addition or loss of H plus, OH minus, H2O, or HX. So like I said, we're mostly going to be looking at turning primary alcohols into aldehydes or carboxylic acids, and secondary alcohols into ketones. So if we look at the oxidation of secondary alcohols, what we're doing is removing two hydrogens from this so that we end up with a ketone here. And one of the reagents we can use for that is this chromic acid reagent. So we put this sodium dichromate and this sulfuric acid together in with our alcohol, and we can turn it either into a ketone if this is a secondary alcohol, or a carboxylic acid if it is a primary alcohol. So the chromic acid reagent is prepared, like I said, by dissolving our sodium dichromate in a mixture of sulfuric acid and water. So we have our sodium dichromate here, our water, our sulfuric acid. This will turn it into chromic acid, which is H2CrO4, two sodiums and these two hydrogen sulfates here. So what happens is we come in with our secondary alcohol, and this is the chromic acid that we just made from up there, and this will attack this right here. This will end up leaving. It will take this hydrogen with it, and so we end up with this chromate ester here, where the chromium is at a +6 oxidation state. So we now have this chromate ester. We have this water come in. It takes this hydrogen. This collapses back down to here, and this then leaves off of here, so that we end up with a ketone here, and our chromium is now in a +4 oxidation state. And we've generated this ketone right here. And of course, we have regenerated some of our acid right here. With primary alcohols, so we can go to an aldehyde or a carboxylic acid. What we'll find is that going to the carboxylic acid is easier, because once you get to the aldehyde, there's nothing that would really stop it from continuing to oxidize all the way to the carboxylic acid. But there are certain reactions, certain reagents we can use to stop at the aldehyde stage. Chromic acid, as I said, generally oxidizes a primary alcohol all the way to the carboxylic acid. So if we put our dichromate in and our H2SO4, this will turn this primary alcohol here all the way to a carboxylic acid. So a better reagent for limiting oxidation of primary alcohols to aldehydes is this pyridinium chlorochromate, or PCC, which is a complex of chromium trioxide with pyridine and HCl. So that looks like this right here. So it's soluble in non-polar solvents such as dichloromethane. So this is good for using on organic molecules. So we take our CrO3, our pyridine, and our HCl, and all of those things together we just call PCC, and we can do this in a solvent of dichloromethane, and that will turn our primary alcohol into an aldehyde. So we're just removing these two blue hydrogens here. And so how this works is we are again going to attack this chromium right here. It's going to have the electrons move up to this oxygen right here. We now have this right here where we have the positive charge on our oxygen. The electrons on one of these oxygens on the chromium will collapse back down. It will kick off this chlorine as a leaving group. The chlorine then comes and does an elimination using this hydrogen right here. That causes this chromate right here to leave, and so now we just have this oxygen right here and the other hydrogen remains, and our chromic acid here is now in the +4 oxidation state, where up here it was in the +6 oxidation state. So we have oxidized our alcohol into an aldehyde by reducing the chromium on here. So we've been looking at the primary and secondary alcohols. So what about the tertiary alcohols? Well, these can't be oxidized unless we break a carbon-to-carbon bond. And this takes much harsher conditions, results in a lot of side reactions. And so we can actually use chromic acid to test for the presence of primary and secondary alcohols. So when a 1' or 2', so a primary or secondary alcohol, is added to chromic acid reagent, the orange color of the chromic acid changes to green or blue. So we're changing the oxidation state of the chromium, and so that will change the color of the chromium compound. And that change in color will then indicate whether you have primary or secondary alcohols present in your solution. And so also, one of the problems with doing all of these kinds of oxidation, whether we're using the PCC or the chromic acid, is that these chromium reagents produce toxic chromium salt byproducts. And so another way that we can use is using sodium hypochlorite, so bleach, in mildly basic conditions for acid-sensitive compounds. So we can use our sodium hypochlorite here in water, and we can turn this alcohol here into this ketone right here. The mechanism for it is we protonate this, so we exchange this sodium for a hydrogen. We do a proton transfer, so we protonate our alcohol here, and then we bring in the hypochlorite to actually do an elimination on the alcohol right here. And so we now have this red oxygen bound, where the green one that we originally had on our alcohol has left as water. So then the water can come in, it can deprotonate here in an elimination reaction. We form a double bond to the oxygen and the chlorine leaves. Then we can bring in another water right here, so we can do an attack on the carbonyl carbon right there. So we end up with this right here. And then we can have another one of our hydrogen hypochlorites here come in and protonate this red oxygen. I guess it wouldn't really matter which oxygen, but here we are looking at the red oxygen. So we protonate that. We then have these electrons on the other oxygen collapse back down. This leaves as water, and so then we can come and have the sodium hypochlorite attack the carbonyl carbon here, so that we end up with this right here. Then our water comes in, we do another E2 elimination using this hydrogen, and this hypochlorite right here leaves, and so we end up with a carboxylic acid. So we have now oxidized this all the way to the carboxylic acid. We can do this as well with potassium permanganate and nitric acid, so these will oxidize secondary alcohols to ketones and primary alcohols to carboxylic acids. So we have our potassium permanganate here, or our nitric acid right here. And so this could turn the 2-butanol into 2-butanone, or 1-butanol into butanoic acid. The least expensive method, and probably what might seem like the most straightforward method to do this, is the dehydration reaction. So just literally removing 2 hydrogen atoms. So a problem with this is that it takes place at high temperatures using copper, zinc, or copper oxide catalysts. And so because this is done at high temperatures, a lot of organic compounds don't actually survive the reaction. So we're going to get a lot of side reactions. We're probably going to break down our organic molecules into other things. And so as such, dehydrogenation is not suitable for laboratory synthesis. So again, all we're doing is just removing these two blue hydrogens here to make a ketone, and then we are losing H2 gas right here. So we can use what's called the Swern oxidation, and this uses dimethyl sulfoxide, so DMSO, as an oxidizing agent to convert alcohols to ketones and aldehydes. So again, we are stopping at the aldehyde here on our primary alcohols. So DMSO and oxalyl chloride, which is this thing right here, are added to alcohol at low temperature, followed by a hindered base such as triethylamine, so that's this right here. So these secondary alcohols oxidize to ketones, primary alcohols as far as the aldehyde. So that's the mechanism we have here. We bring in our alcohol, our DMSO, and our oxalyl chloride, which is this COCl2 right here. And so then we generate a ketone or aldehyde. This is turned into dimethyl sulfide. So this is losing its oxygen there. We generate 2HCl here, and we also get carbon monoxide and carbon dioxide products there as well. And this is the way that you'll usually see it written, like if you're seeing this in a synthesis. So it'll have, as the first step, we're adding our oxalyl chloride here and our DMSO. Then in a second step, we're adding our triethylamine right here. That turns the alcohol into a ketone or aldehyde. There is also oxidation using what's called tempo, which is this long molecule right here. So it's usually just called tempo, and it contains a stable radical on an oxygen, which can be used along with sodium hypochlorite to oxidize primary alcohols into aldehydes. So again, we want to turn our primary alcohol into an aldehyde, and we can use this tempo here to do this. So we're bringing in the sodium hypochlorite right here. We have this radical intermediate right here, and so with this active species here, we can actually do the oxidation of the primary alcohol into an aldehyde that will turn this right here into this right here. Then we regenerate our active species here using this mechanism. So we lose an H plus. That gives us this right here with the radical. We bring in the sodium hypochlorite to regenerate the active species there. So this is just a summary of the oxidations we've been talking about, except this one down here is missing the tempo that I just talked about. But we see we have several choices when we want to do these oxidations. So if we want to do the harsh oxidation, so if we don't care whether our primary alcohol turns into a carboxylic acid, or I guess more likely if that's what it is we're actually trying to do, then we can use this. So we talked about this one right here. So this is the sodium dichromate and H2SO4. We talked about the potassium permanganate here. We talked about this sodium hypochlorite right here. We can also use the chromic acid or the CrO3 plus H plus. So those are all going to give us the full oxidation, where some of these that we can use can stop at the aldehyde when we do it on a primary alcohol. So we talked about the PCC and the Swern here, and we talked about tempo, which isn't actually on this list right here. So these are all ways that we can oxidize alcohols into ketones, carboxylic acids, and aldehydes. And of course, there is also reduction of alcohols. So this is not often used since it removes functional groups, and functional groups are the things that we are interested in when we're trying to do chemistry. So one thing we can do is we can just do an elimination of the alcohol. So we remove this hydrogen and this OH right here. We form an alkene right here. Then we can just do a hydrogenation to turn it into this alkane right here. Or we can tosylate it here, and then we can bring in something like lithium aluminum hydride, do an SN2 with the hydride, and generate this alkane right here. So that is reduction of the alcohols. And so I've made this little cheat sheet here of a lot of the oxidations and reductions that we can do with alcohols. So we can start over here. If we have an alkane, we can do radical halogenation. Then we could do some kind of, say, SN2 reaction with an NaOH to replace the chlorine on it with an alcohol group. And we just saw here, this is the reduction of our alcohol back to an alkane. If we want to oxidize our primary alcohol into an aldehyde, we could use something like PCC or the tempo and sodium hypochlorite here. If we want to turn an aldehyde into an alcohol, we could use something like sodium borohydride or lithium aluminum hydride or rainy nickel right here. But if we just wanted to go to the carboxylic acid, we could use our sodium dichromate and H2SO4 here. And of course, we could use that on an aldehyde to turn it into a carboxylic acid. And we could turn an alkane into a secondary alcohol here. So now we're doing radical bromination here because we want to get this on the secondary carbon here rather than on a primary carbon. And so then we could just do another SN2 with our NaOH here. And if we wanted to reduce this, we could tosylate it, use lithium aluminum hydride to turn it back into an alkane. And of course, the secondary alcohol, we can use things like PCC or our sodium dichromate and H2SO4 to turn it into the ketone. The ketone we could turn back into an alcohol with sodium borohydride or lithium aluminum hydride or rainy nickel. And we see we can turn a ketone into a primary alcohol by using the Grignard reaction. And so this right here, so I said before that there isn't a way to oxidize tertiary alcohols, but I have seen some sources that say this can be done with potassium permanganate and H2SO4 because potassium permanganate is such a strong oxidizing agent that you might be able to maybe get some kind of reaction from that. And we could do a reduction of our 3' alcohol using H2SO4 and heat to get the alcohol group to leave in an SN1 reaction. And then we could generate a double bond on here. Then we could just reduce that double bond into an alkane using our hydrogenation here. So this is, as I said, just kind of a little cheat sheet of some of these popular reactions for doing these oxidations and reductions of alcohols. Anyway, I hope you found this video helpful, and I will see you in the next one.